Hello, let us begin by defining two types. So a cat has a name which is a string, and the deriving wrapper allows us to print cat to screen. Similarly, a dog also has a name which is a string. After these type definitions, we can create cats and dogs with specific names using the following constructor: cat.mk with Tom as the name produces a cat named Tom, and dog.mk with the name Pluto produces a dog named Pluto. We define a class animal. So a class classifies types based on their properties. So here we say that a type A is an animal if there is a function sound that maps A to string. We can say that a cat is an animal by using an instance declaration, and we define the sound function for cats as follows. So we print the name of the cat followed by the word mews. Similarly, a dog is also an instance of the animal class, and we do something similar to define sound for dogs. Once we have these definitions, we can evaluate the function animal.sound on cats and dogs. So if I evaluate animal.sound on a cat named Tom, it will print Tom meows. And if I evaluate animal.sound on a dog, it prints Pluto barks. Observe that the sound function here is different from function like square we defined earlier. Here we have two distinct definitions for sound depending on the type of the input. We will now do some group theory. So we start a new section. And we define a group as a class. So we say that a type G is a group if it satisfies all the properties of groups. So it should have an operation that takes two group elements and produces a group element. It should satisfy associativity for the given operation. So multiplying A with P and then with C should be the same as multiplying A with the product of B and C. A group must have an identity element E, which should satisfy the identity property, which is that for any element A in G, A times E is equal to A and E times A is equal to A. Every group element should have an inverse. So every A should have a B such that AB is equal to E and BA is equal to E. This is not the most minimal definition possible for a group, but we will use this for convenience. We open the group so that all names in group are accessible directly without the group dot prefix, I define an infix operator star, which is the same as op. I define a predicate is identity on a group G for an element E prime in G as for all A in G, E prime times A is A and A times E prime is also A. Notice the square bracket syntax to constrain the type G. Now we can prove the theorem unique identity for a group G, which is that for all E prime in G, if E prime acts like an identity, then E prime is equal to E. Observe that the goal is a for all, so we can introduce E prime into our hypothesis, and also the left hand side of the implication, which is identity E prime. So we will call that H. And now we have to prove E prime is equal to E. So we specialize H to E to obtain E prime E is equal to E and E prime is equal to E. Observe that E prime E is equal to E. So we need a way to start from E prime and end up at E. So we enter the calc mode and write E prime is equal to E prime times E because if you apply the identity axiom to the element E prime and take the left part of it, you get the equality E prime E is equal to E prime, and if we take eq.sim of this equality, we will get the proof of the first step. Observe, we specialized the identity axiom with A is equal to E prime. We can explicitly say that E prime has type G using the following syntax to clear this error. So Lean isn't able to figure out that E has type G from this context. Next, we say that E prime times E is the same as E by taking H dot left. and this finishes the proof. We will now go ahead and prove the second theorem, which I call left cancellation. It says for a group G, AX is equal to AY implies X is equal to Y. If we enter the tactic mode, we see that there are 3 for all quantified variables and the left hand side of an implication. So we introduce all of them into the hypothesis. Now we obtain the A inverse using the inverse axiom for the group G. Observe, AI is in G and AI satisfies all the properties of inverse, and the proof is named AIH. Now we do a series of rewrites to go from X to Y. First, we write X as A times X. By using the identity axiom. Now we rewrite E as A inverse A by rewriting it with AIH dot right. We now use associativity to write this as AI times AX. We use the equation AX is equal to AY to rewrite this into AI times AY. We again use associativity to rewrite this into AIA times Y. This time we are taking the associativity axiom from right to left. So we have to take the symmetricity of equality to get this. We now reduce AI times A into the identity element of the group. This is given by AIH dot right. And finally, we use the identity axiom to rewrite EY into Y. Here identity Y dot right is the right hand side of the identity axiom for Y, which is an AND. And observe that we have now finished the proof. Thank you for watching. Bye.